Hey, good morning, everybody. I hope everybody's doing well. In the event that you didn't see the email that I sent out over the weekend, the way this week is going to work is we're going to have the normal lecture today. I'm going to move the lab to Wednesday. So we're going to have a lab Wednesday instead of a lab Friday, and then Friday's lecture is going to be canceled to have a little bit of a mental health break to be able to address other stuff in your other classes. The way that the final 2 weeks will work is on the Monday and Wednesday, we're going to explore using the advanced C++ standard template libraries to be able to solve more advanced computational thinking. We have a final homework assignment and then a lab to be able to strengthen those skills. And then on the Wednesday of the last lecture, I will be reviewing what we've covered in the class, and then we will go over a final exam review. And that would be the general. So we've got 3 weeks left. We're almost there. So I'm canceling the classes. I'm aware that there's a lot of stress going on. It's possibly the most stressful semester for students ever, at least since World War II. And I mean, I'm serious. Like, you know, when I see students who are really stressed out or coming to my office, I have to remind myself that I get to go home with my wife. I get to go home with my dog. Right? One of the reasons why I brought in Aaron on Friday, it's a little bit of home for everybody. So I'm very aware that this is a very stressful time for everybody. And so that's why I'm kind of rearranging the class. But there is a unpleasant thing that I need to talk about really quickly before we begin. So a few of you might have gotten an unpleasant email from me this morning. So when you submit the assignments, I run a program called MOS. It's a program that's developed by Stanford, and it's used to check for plagiarism, copying other students' code. And up to this point, I hadn't had any instances that I thought we were ready to talk about. And on homework 6, there was an unfortunate spike. The reason why I feel compelled to mention this to the entire class is because we're all engineers or aspiring engineers or scientists, right? The reason why it's important that we have to think about academic integrity is not because I'm trying to keep some sort of fairness among the class, which of course is important. The reason why is because when you receive your diploma, like I have my diplomas, right? It's not just, hey, you have a set of skills. It's also a recognition of your responsibility to society. And our responsibility to society is to do good and honest work, right? So when we are submitting assignments, so when you're submitting some assignments in my class, every single one of those submissions is practice for the real world, not just in terms of building your coding competency, but demonstrating to yourself that you can handle it in an honest manner. And where that line is typically confusing for students and where it's important to make that line clear is when you're working together and you might be passing code back and forth between each other. There's a reason why we have to be firm on this. And the reason why is because lazy copy and paste is the source of so many engineering disasters. It's not just about, do you have code working that you understand? It's that I need you to actually type it and actually think it and put it in. I'm giving you a really quick example. How many of you are familiar with the Kansas City High Regency walkway flags? All right, so we've got 2. So can you guys give me a general idea of what you know about it? Yes. Okay, so you've hit on some of the details. What are some of the other, what were you about to say? Okay, so you've hit on some of the crucial details. So it actually happened about 1989, and it's a walkway that was above. It would be kind of like if this was a hall, but we had another walkway on top of, where several students were also watching down on us, right? And it was basically used for this big ballroom. The hotel had just opened, and this walkway was used with these certain rods. And what happened is that one of the engineers just lazily copied and pasted a different design for these rods. So instead of having all the pressure go in one location, instead of having distributing the pressure so that way where everybody was standing didn't get distributed into one space, it should have been distributed evenly so that way it didn't bring everything down. So what ended up happening is that they had this big party of the opening of the hotel and the whole walkway collapsed, right? And 250 people were killed, about 500 people were seriously injured. The unfortunate reality is, as scientists and engineers, we can seriously harm society and people with a lazy attitude and a pen, right? The reason why it's important to bear in mind when you're doing some work, you don't want to just copy from a source, you don't want to copy from your friend. The reason why we're so adamant about this is not because of your grades, and it's not because of who's going to get the best GPA, who's going to get the best job. It's because we are going to be writing code or putting our work into machines, into buildings, into chemicals, whatever it is that you end up doing, that people are going to be reliant upon. For the engineers who built this building, we walk in every day and we are reliant upon the fact that they did good and honest work to build this ceiling, right? If it collapsed upon us, if they did lazy copy and paste, and we were all killed, or our parents and families wouldn't care that much if the engineer said, well, I was really stressed because it was a pandemic, right? They would care zero, in fact. So that's why I want to mention this to the entire class. I'm going to use this as a mentorship opportunity. I understand it's an extremely stressful time of year, and the fact that it just jumped up like that tells me that there's stressors going on and that this is not like normal behavior. That being said, I want to make it clear that if you're working together with somebody, this is what I used to do when I was in school. If I was working together with somebody and one of us didn't understand it, we might explain it to each other, we might look at each other's code, but what I would do is I'd say, all right, to make sure that I understand it, I'm going to write it on my own. I make sure I'm explaining it and it's going through my fingertips. If you can do that, I don't care how much you work together with everybody, right? Because ultimately it came from your brain and went into the computer, right? If you can't do that, if you're copying other people's code, that's where we have to address those issues. All right, so I apologize for having to go on that little spiel, but I felt it was important to simultaneously let you know that I understand that this is extremely stressful time, but we also have responsibilities to society that we need to be mindful. So thank you for bearing with me on that. All right, so what we're going to do is we are going to build something called a singly linked list. And a singly linked list is a fundamental kind of data structure. And the reason why it's very useful for electrical engineers, mechanical engineers, aerospace engineers, chemical engineers to understand linked lists is because linked lists are good for trade-offs in memory. A lot of you will be writing programs on embedded systems and will need to understand how to write low memory applications. So arrays we have static arrays. So we learned about static arrays, we've learned about malloc, and the new keyword in C++, and it allocates an exact amount of memory, right? Excuse me. So when we use malloc and we don't know the number of elements beforehand, so let's say we have a scenario, we've gone over this, right? Where we insert a certain number of elements and we have to calculate a median. We've done that in the assignment. In C, before we were learning about dynamic arrays or vectors, we had to set the cap at 25, right? So you say until 25, so then you would allocate an array of a length 25, and that's how we would be able to solve the problem. So the question is, well, what if we don't know the number that we have to find the median on? So let's say I want to find 56 or 72 or 8. How do I be able to account for this? And furthermore, when I'm done with one of those, how do I delete it? The issue in a vector is that when I have a certain number of elements and I want to delete an element in the middle, I have to go to that location and move the rest of them over. That's why when you call the erase method in standard vector, you have to go dot begin plus, because you have to move it over and it has to move all these things over that way. So the solution comes around, the first solution comes around in 1956. And a company called the Rand Corporation, they were trying to figure out how to just put things together. They understand pointers, they understand this idea of classes, or being able to put things into structures, and they called them nodes. Oh, sorry. They called them nodes. And the whole idea of nodes is that the node contains a piece of information. We know that the address of a piece of information in the heap is where the pointer points to, right? So then we have a specific location, and we've learned from our understanding of structs and classes that the next piece of information can be data. So here's the interesting thing. The next piece of information we could put in a node is another pointer. And that pointer can contain the next node that we want. So therefore, I can start inserting nodes to link to the locations in memory. And to the moment I need to put in a new element, I would just insert it by allocating that pointer in the last node to a new location in memory, and then putting in that piece of data there. Okay, does that make sense? So in general, what we want to do is we are going to only have enough nodes to contain the information we need at any given moment. Yes? Oh no, this is just one piece of information. So for example, this could be an integer, right? Yes, yeah. Yeah, so it's like an array, except the pointers between each element are telling me where the next piece of information is. So the way it would work in a heap is I would have a piece of data, and then the second element is a pointer, and that could point down here where I have a piece of data, and I've allocated a pointer, and that could be somewhere else, depending on what's available to me. So one of the benefits of a linked list is that when you have very low memory applications, you can use this and it'll say, all right, allocate memory, and it'll find the next available piece of memory for you. And if there's enough, it'll say, all right, I can allocate more memory. And you can use this to find them all. And what we're going to see is we're going to see that we can allocate what is known as a head pointer that's going to tell us where the very first node is. Does anybody have any questions? Let me let me check the chat, and then I'll see if you. Yeah, what's up? What's your question? So you're getting to a discussion we're going to have a little later about when it's a good idea to use linked lists as opposed to vectors. Hey, does anybody have any other questions? All right, so the advantages. Each element keeps information on how to locate the next element. And if we want to insert at the front, it's going to be what we're going to call constant time. Now, next week, we're going to learn about something called big O notation. That's going to be a way of quantifying how fast the program runs. When we say something is constant, meaning that we're not dependent upon anything else, we call it big O of 1, some sort of constant time. And it can store the exact number of elements when the problem is not known at the beginning. So the disadvantage is they're ordered in a strict linear sequence, meaning that I have to go to one, then I have to move over to the next one if I'm trying to figure out if something's in there. If I want to go to the end, I need to go through each node. So it would take the number of elements that we have in there and we have no direct access. Like in an array, we have direct access. I can use the array operator to say, give me the 8th element. Right? In a linked list, we don't necessarily have the ability to do that. So these are kind of the pros and cons. Okay, so the first thing I want to do is I'm going to first show you some code, and then I'm going to show you an animation on how it is we're just going to create a linked list node. So first, I have this code SLL node, right? And in SLL node, every single node contains a piece of data and a node pointer to the next node. Okay? So basically what a node pointer, breaking this down, and this is where me kind of really emphasizing at the beginning of the semester about void pointers and how the operating system takes this idea of a void pointer and you can cast it to another type, really becomes beneficial. So here, a node star with a template, and I call it next, that's just 64 bits. It's a void pointer. That's all it is. But we tell the operating system to interpret that as a node pointer. And in this case, when we use a node, the memory is going to contain the data and a pointer. So now to get back to Henry's comment, the question becomes, when would we want to use this, and when is this piece of data and the node beneficial? It ultimately depends on what it is that you are templating the linked list to. If it's small, like for example, if it's integer, let me do a quick math problem to show you what I'm talking about. So if it's, let's say I have 17, I want to have 17 integers, right? So I have 17 integers times 32, and that's the number of bits in each integer. And then I have to have 17 next pointers, right? So that becomes plus 17 times 64. So if any, no, let me bring up my calculator here. Yeah, it's not going to work out. 64. 17 times 32 is 544. 17 times 64 is going to be 1,088. So I just add them together. All right, so that's the number of bits that would be in a linked list, right? So if we were using a dynamic array, we just went over from 16 to 17, right? So in order to do this, we would have 32. So this becomes 32 times 32, which is 1,024. So in this scenario, the dynamic array wins. So even though I'm doubling, that becomes helpful. But now let's put in 64, right? So that's 17 times 64 times 2, right? So that becomes 2,176. And so now this becomes 64 times 64. And that becomes 4,096. So already, if we go from an integer to a long integer or a double, if we have a linked list of doubles, then now our linked list is winning. Does everybody see that? So in my data structures course, I have a team that is working with a company called GE Healthcare, and they're doing constant monitoring of CAT scans. And they are received, I forget the exact number, but it's something in the ballpark of 500 pieces of data every single time, right? They received 500 pieces of data, we calculated it out, and it was 500 times 64, and that was in each node, right? So it becomes 500 times 64, and that's the number of bits. So that's, let's say, I'm going to say 500 times 64, and that's equal to 32,000. And so now if I have, let's say if I have 50 nodes. So if I have 50 nodes, this becomes 32,000 times 50 plus 64 times 50. So this becomes 1.6 megs. And this becomes 64 times 50. Actually, I'm going to use 17 again because that just makes much more sense. So 32,000 times 17, that's 544,000. And then 64 times 17 becomes 1,088. So now this becomes 545,088. So now if we do 32,000 times 32, which is what would be our dynamic array, because we've gone over by 1, so now we had to double it. 32,000 times 32 becomes 1,024,000. So when we use a linked list in this scenario, it's only 53% of the memory. So in that scenario, we were able to, by making a choice, in this case between a linked list and a dynamic array, we were able to cut it down by 47%. So Henry, does that address your question? And so this is kind of a precursor into, we do all kinds of, in the data structures course, I know several of you have asked me about that class. In the data structures course, we do all kinds of things into going down into trees and hash tables and tries and all kinds of crazy things to choose the right situation to apply this computational thinking that you learn at the fundamental level to more advanced concepts. So let me get rid of this. That would be a good slide for me to add in the future. So we have our data and we have our node pointer. So the first thing I do is I have this function, and then I have this class method check memory. And so now what we can do is we combine everything we've learned so far this semester, plus potential applications in a low memory environment that you might encounter to see what this is doing and why it's working. The check memory method says if this equals null. So remind me, what is the this pointer? Does anybody remember what the this pointer is? Yes. Exactly right. It points to the address of the number on this data heap, right? So what ends up happening is if it's pointing to null, what does that mean? There's nothing there. So what's going on is I have tried to allocate memory and the computer said you can't. The reason why this happened is because we are out of memory. So we are out of memory and we end the program. Does that make sense to everybody? So what we're going to do next is we have a constructor for the node. Here we have our member initialization list. We have the data that calls the default constructor for that data. So if I have a huge class, then it's just going to call the default constructor for that class. And I initially set the next pointer equal to null, because as of right now, it's just a node. It's not pointing to anything in the linked list. And then inside of that, I call check memory just to make sure that the memory is available. The next constructor I'm going to show you is going to be virtually the same, except we're going to read in a piece of data. And all we're doing is we're setting the data in the member initialization list equal to data in. Otherwise, it's the exact same thing. So here we have an overloaded constructor that allows us to be able to construct a node when we have a piece of data. Yes? Okay, the good question. So the question is, for those of you on the chat, is there a way to go back to the previous one? In a singly linked list, there is none. So that is the challenge of the singly linked list. And if we had a lot more time, we're going to, when we covered in data structures course, we would talk about something called a doubly linked list, where you're able to go forward and backwards. Now the question is, if I wanted to go forward on a singly linked list, how could I potentially go back? Singly linked lists use a lot of recursion. We're going to show some examples of that today. So we're going to take advantage of our understanding of recursion to be able to manipulate singly linked lists. Did I address your question? Awesome. Any other questions? Okay, so I have a destructor, and all it says is delete next. Now, you may not see it yet, but I'm going to show you an animation. This is me taking advantage of recursion. And so that'll give you a little bit of a preview here. I'm just calling to delete the next node. Copy constructor, I have a node that I'm calling by reference. And I say data is equal to copy data, next is equal to copy next. And then I have an assignment operator for a node. I say if this is not equal to the address of assign, we copy the data and we copy assign.next. So now that you're familiar with inheritance and polymorphism, what's going on here is making a little more sense, because we have an object that we're creating that we are going to copy over and then return a dereference pointer to this, so that way we have it on the left-hand side. So now what I would like to show you, and I want to go into a little more detail about what it is I'm doing here and why, is that I have yet another operator. And this one, instead of returning a call by reference to a node, it's returning a pointer. And so what's going on here is I'm passing a node pointer. And then instead of what I was doing up here, I said this data is equal to assign.data, right? So everybody see that? What's going on down here is I am now getting, I'm dereferencing the pointer in order to get that information. You may also notice here that I'm saying that this is not equal to a void pointer, the address of assign. So now let's apply what we've learned earlier this semester about void pointers and why it is that we can use this advantageously in our systems. So what is going on here is that at some point, I'm going to have a node, right? And I'm going to say that its next pointer needs to point to some other node. So we're setting up for that. So I'm going to say that next is equal to temp. So here, let's just say node next is equal to temp. So I'm now pointing out that I have some sort of next pointer pointing to the next location. Now here's what's going on. First, this becomes really important because we don't want any self-referential nodes. The second part is when I have this pointer, this data is equal to assign data. I'm now passing a node pointer, and when I make that equal to it, I have now defined the object's behavior. So what's going on is I'm saying, all right, I want to point to this location and I want to point to that value. And then we return that pointer as well. So this is, I'm going to point out when we do constructors and operations in the singly linked list, how this is going to become really useful. So here I have operator is not equal to, passing the pointer, and I'm just saying this does not equal to void star of the address of RHS for right-hand side. And that's the end of the node pointer of the node. Yeah. Yes. Yeah, it's not equal to. Well, A does not equal B, it should return a Boolean by default. Hmm? Well, technically it isn't, it can be an unsigned integer, but I would strongly recommend using a bool because a bool will only allocate 1 bit. Whereas an unsigned integer will do 32 bits. Yeah. Any other questions? All right, let me check the chat again. All right. And so here's what's going on. I would be creating, move this up here. I'm creating a piece of data and it's just pointing somewhere for now. And I showed you all these, the constructors. I followed the rule of 3. Here I showed the node pointer and the not equals. So I showed you the node star assignment. And here I have to check here for not equals because I'm going to do comparisons later on when we do insertions and deletions. So with linked list initialization, here's what's actually going on. In the singly linked list, I'm going to call a new constructor, and I am going to have a private member of a node pointer that I'm going to call head. And that's what I'm going to initialize in the default constructor of the singly linked list. And then what I'm going to do is I'm going to set head equals null. So this is where the assignment operator first comes into play. I pass it and I say null, and as of right now, the singly linked list is empty. And if the head pointer is pointing to null, then it is an empty list. Otherwise, it has elements. Next, let's say I want to create a new node. So here I have node t star temp. So I've templated the node pointer to equal a value. So we use that new keyword that we learned about last week, the new node value. So now I'm creating a node location and I have a pointer to it, right? So that becomes beneficial because I don't need to create a new variable to store that location. Because if I have a temporary pointer and I want to link it using the head pointer, for example, I can just reallocate that and I'll be done with it. So I'm reducing the amount of memory I'm using. So when I do node t data in, I'm creating that node value. And just like before, we're using the memory. And then I create the next pointer. So this point, the next pointer is going to be null. And so what I'd like to do next is show you the beginning of the singly linked list class. In the singly linked list class, what's going on here is I have the private member of the head node. And in the constructor, initially, if there's nothing in it, I just, in the member initialization list, set the head equal to null. And then in the destructor, I'm going to say delete head. I'm going to show you a slide in a little bit that shows you why this is actually recursion. So I have a copy constructor. And in this copy constructor, what I'm doing is I set previous is equal to, actually, you know what, there's animations. I'm going to show you that in a moment. Okay, so all I need to do is show you the constructors right now. I apologize. So here's the thing with the recursion. So we learned about this delete keyword, right? In the delete keyword, what I'm doing is I am going to free that memory after I do whatever is inside of the braces, right? So in the inheritance and polymorphism lecture, you were able to see that you could print out constructor and destructor inside, right? So there's things that you can do inside before that memory is freed. So on the left is where I have the singly linked list destructor. And here on the right, I have the node destructor. When I call singly linked list, delete head, is going to call the destructor for that node. So everybody see that? Then what's going to happen is it gets to the head node and it's going to delete next. So what do you think is going to keep happening? Say I have several nodes, yes. All right, very good. So it's going to keep calling these. And so you made one, I'm going to change one quick thing in what you said, right? Because it's an important distinction. What's going to happen is it's going to call every single destructor, and then when it hits the next null being null, it's then going to work its way back up. So it's actually going to be recursive in nature. So here's what's going to happen. I'm going to go through the animation here. I call it delete head. Once I call it delete head, it's going to call the next here, and that one's going to call the next here, and it's going to call next again, and that question mark I have represents null. So once it gets there, it's going to say, okay, I'm done. So now I'm going to work my way back up, and when I delete, I'm going to free it off the heap. I'm going to free it off the heap, and I'm going to free it off the heap, and then I'm going to delete the head pointer. So that's a simple way of using recursion to go back and forth along singly linked lists. Does that clarify some of your questions from earlier too? Awesome. So now I'd like to go back to those to the code and show you the rule of three. My apologies. Let me scroll back up here. So here I have a copy constructor, and I'm calling a singly linked list by reference. And what I am doing is I'm creating a previous and next pointer. And so the reason I'm doing this, and we're going to see animations where I do what I call the walk in a moment. What's going on is I'm iterating through, and while the current is not pointing to null, I'm going to insert that data. And so the reason why I'm going to insert the data is because if I have a linked list of 3 elements, right? What's happening is I want to create a new linked list. So I only want to copy the data. I don't want any pointers between them. It's a common mistake when working with these kind of structures to accidentally say, I want to make this pointer point to the next location. So in this case, I'm calling this insert method, which we're going to go over in a little bit. And then what I'm going to do is I'm going to kind of walk through. Now, the reason why I'm doing this is because current is going to keep going until current is null, and then we're going to stop. So this notation, what's going on in the linked list is I have a next pointer, right? So what's going to happen is I have a cur pointing to that particular node. So cur is its own node. And I have another node here, right? So when I say cur is equal to cur next, and I have an animation where this is going to be shown clearly as well, what's going to happen is it's going to go cur next is the address, and then it's going to update it to point to this node. So that allows me to keep moving along. And you're going to do the same thing in the assignment operator. So here is the linked list initialization for insert. And this idea of previous and current arrow next should hopefully become clear. So when I insert the first element into a singly linked list, what's going to happen is I'm going to call this line of code temp is equal to new temp value. So I am creating a temporary node that is somewhere on the data heap. And then I'm going to call a method isEmpty. All method isEmpty is doing is saying if head equals null, which is why we have to do the comparison. So when it's not, if it is null, that means it's not pointing to any nodes. So what's going to happen is if it's empty, and in this case it is, we see that in the small green circle, what's going to happen is I'm going to set the address that's being pointed to by the head pointer equal to the address being pointed to by temp. Does everybody see that? So now we have an element and then we're done. So now we're going to go into our second insert. Our second insert, we're going to create another node. Is it empty? It's not, because we have something that we're pointing to. So then we're going to start creating these pointers. So we have previous is equal to null, and cur is equal to the head pointer. Does everybody see that so far? Here's what's going to happen. Until we get to the end of the singly linked list, what's going to happen is I'm going to say, well, cur is not equal to null. So I'm going to set previous is equal to cur, and cur is equal to cur next. So now we have while cur is equal to null, and in this scenario, cur is null. You see that? Because we're pointing at the end there. So this is why we have to keep a previous and a current pointer. Because if we hit null, null just means we don't know where it is in memory. The previous pointer knows where the node we need to insert it is. So this is the node that's currently in the linked list, and we have to have it point to this node. So the way this is going to work is it's going to say previous arrow next is equal to temp. Does everybody see that? So this allows us to be able to update this. So when you see this in the slide, we see that it'll update, and then there's the green for everything that I just drew out. Previous arrow next is equal to temp, and we're going to see the arrow at the end go out. And then when we give the braces, what's going to happen is everything, the previous and cur are going to go out of scope, and now we are going to have our single. So now I want to do a third insert to kind of go through this process again, and just to show you that previous cur walking in a little more detail. We're going to create a temp pointer. We're going to check to see if it's empty. It's not. Previous and current. While cur is not null, I'm going to set previous is equal to current and cur equal to cur next. Still not null. Previous is equal to cur is equal to cur next. So you see how it's kind of what I'm saying when I say it's walking along, because we got previous and cur, it's like two legs. So now cur is equal to null, and now we do the same thing. Previous next is equal to temp. And then we go out of scope, and then start. Yes. Oh, because they are all pointers. Because when we do this, what's going on with previous and cur here, since they are node star T, all they are is 64-bit values that are used as pointers. But since they are defined and we have a class definition, we need to dereference them in order to be able to get that information from them. Okay, cool. Any other questions? Right, so is empty, as we saw, head equals null. And now contains, what I'm doing is I'm doing the same thing. I'm walking through. I think it might be more clear if I go into the actual code. Okay, so here what I'm doing is I have const t ampersand search val, and it's a const method. So if it's empty, I'm going to return false because, well, if the list is empty, it could be anything, and it won't be there. Otherwise, I'm going to do the same thing. I'm going to do the walk process, except I'm going to add a second thing here. I'm going to say cur does not equal null, and cur data does not equal search val. So there's a reason I do it in this order. First, I want to make sure that the memory exists in the first place. Otherwise, you're going to get seg faults and it's going to be really unhappy. So whenever I'm doing these things, I want to check for a stopping point. always do the null test first, and then any data comparison test. Okay, so that's why. So if I took that out and I get to the end, it'll segfault. But if I say if cur does not equal null, then it's pointing at nothing, which is what I want it to do. And it's like, oh, there's nothing there. Well, we're done. But if I don't do that, it's just going to keep going to the next place, and then it'll segmentation fault. So then I keep doing the singly linked list walk. And then if we have stopped, there's one, well, we have to stop in this case, I've guaranteed it. But there's one of two scenarios. Either we've reached the end of the list and it's null, or we are, we have found it. So if we haven't reached the end of the list and we're not at null, then we have guaranteed to found the element. So here's another type of insert that will be very useful. It's called push front. And when we go over the standard template libraries, you're going to see that no matter what I do for insert, it's going to take a lot less time. So what happens is I'm going to create a temp value. And then what I'm going to do is I'm going to say, I'm going to have that temp value point to the head. And then head is equal to temp. So in this case, head is currently null, so it doesn't do anything, right? But now let's say we have a non-empty list. So what's going to happen is, just like before, I'm going to create a new temp pointer, right, a temp node, and then I'm going to say the temp's pointer is equal to the head pointer. Does everybody see that? So this kind of follows up on the question that Jake was asking earlier. So in C++, we use these pointers as a way of saying we don't need to allocate another register like we had to do in C. The temp node pointer can contain its own information if we allocate it. So what's going to happen here is I've allocated with the new keyword, which gives me the memory to have the data. Otherwise, if I say it's equal to null, like we did with previous, then it's only going to be a 64-bit value. When I say temp next is equal to head, it's now pointing to the previous head location, which means if I point to head with, if I make head is equal to temp, it's now going to update to that. And then this becomes really beneficial because if I just insert it, I don't have to go through every single element. I just put it at the front. So when singly linked lists are used, they're typically used in scenarios in which I can either put it at the front or I can sort it, which is what you're going to work on in this week's lab. So what I would like to do for the remainder of the lecture is talk about the delete method, and I'll start out the beginning of Wednesday's lecture by finishing up whatever it is we don't discuss here. But here, what I do is I create a previous, a cur, and then I also create this temp node. And what the temp node is at the end, after I've moved all the nodes around, the temp node is going to be pointing at the node I want to free. So first, if it's empty, we don't do anything. So now I have a head node. And what happens is I'm going to create a temp node, previous node, and a current node. And if it's empty, otherwise, here I have target is equal to head data. So what's going on in here is the target here 12 is equal to the node of the data. Does everybody see that? So what's going to happen is it's going to say temp is equal to head. This is the first one. Head is equal to head next. So in this case, now we're making it null. And now we're going to free temp. So now that memory is gone. And then here I just have return true to indicate that we successfully deleted the value. For this case, 8 is at the end. So we're going to skip past the head node case and go straight to the last case. What we're going to do is we're going to previous is equal to head, cur is equal to head next, and now I'm going to iterate through, do the walk, and now I've matched it. I found the target, and I say if cur is not equal to null, then temp is equal to cur, and then, and this is this is a good place to kind of leave off on. Previous next is equal to cur next. So what's going on here is cur next is pointing to null, right? I'm going to make previous next point over here. to skip that previous node, the node we're going to delete. And so what's going to happen, we're going to see that the node pointer is going to go past, and then I'm going to call free temp, and now that memory is gone, and then we go out of scope. Here, really quickly, it would go all the way through. If cur is equal to null, that means we went all the way through the list and our target wasn't found. And so what I'm going to quickly do, and I'm going to go over this in more detail on Wednesday's lecture, but I'm going to call make SL list and just a SLL test, excuse me. And then I can put in several elements. I'm going to put in 10, 7, 14, 13, 9. And I'm going to go over more detail at the beginning of the lecture. But what's going on is it's inserting those elements in the order that I put them, as putting them on the back. So if I say value to be deleted, if I say 14, it's going to successfully delete that element. If I delete 10, it'll successfully delete the head node. If I delete 9, it'll delete the element at the end. If I do 15, it'll say it was not in the list. If I delete 13, then delete 7, and then it'll tell me that the list is empty. So I'm going to show about how that's done, and then I'm going to describe what I want you to do using inheritance and polymorphism to make a sorted singly linked list on Wednesday. You all have a wonderful day. Yes. No, it will be due on Monday as normal.